X, Y, and this is my Z. Okay. So this is my over here. This is my T, right? Then we have a length over here. This is our point A. This is our point B. Then we have a Z component. Right? So the distance between here to here, this is my width of cut, okay, or depth of cut, either one. So the area of the shear plane is this area over here. Okay, so this is area of shear plane. And the shear plane is controlled by the what? By the shear angle. Okay, so LAB, so we know mathematically it's so straightforward. LAB, right, is equal to T over sine what? Sine pi. Okay, so area is equal to LA or T W over sine pi. And the width of cut is W. Okay. So we're going to come up with a very simplified calculation, okay, for cutting force. Very simplified. So the cutting forces, right? The cutting force is equal to the shear stress, right? Shear stress multiplied by the area of shear plane. Okay, so this is area of shear plane. Right, that is our area of the shear plane. So when we put this in, we get what? Tau, right, multiplied by T omega over sine pi. Okay. So we're going to assume, we're going to make an assumption. Okay, we're going to make an assumption. Do that with your ice cream, okay? Positive rate and negative rate and see what happens, okay? Or with your butter when it's a pancake day and see what happens. Then we're gonna so we know that T and omega, they are known as what? Process parameters. So process parameters means you set it up and it's a constant. Okay, so these are constant. Right? And then we're gonna assume, yeah, we're gonna assume that we're gonna assume shear stress, okay, is also a constant. But right, it will change, okay? How much? Depending on the material. So we gotta assume that it's gonna be constant. Okay, it's not gonna change significantly. Okay, so we're gonna draw a table now. Okay, so this is alpha rate angle for positive. So that is rate angle for negative. So we make some assumption that the shear stress, right? The shear stress over here, right? This is our what? Constant. And from our figure, as we've seen before, right? LAB, right? The length of AB for positive rate will be lower, for negative rate will be higher, right? So if you look at area of shear plane, right? So when the length is lower, the area of the shear plane will be lower because W over here is a constant, is the width of cut or the depth of cut that you decide to use, and this will increase. So that is why over here, if you look at forces, forces is equal to shear stress times by the shear plane So for this case, if you compare both of them, the shear force or the forces will be lower for positive rake and higher for negative rake. Okay. So we can draw another trend from here, right? We can draw another trend. So another trend that we can draw is if we look at if this is our alpha, right? This is 0. This is negative rake. This is positive rake. So we can draw for LAB, the length of the shear plane, or the area, okay, not comma, or both will have the same trend, or area of shear plane, right? So negative rate will be higher than positive. So this trend over here is very similar to your what? Forces. Okay. Then I'm going to draw one more trend that is acquired experimentally. This one is again acquired experimentally. So it's going to be the proportion of heat flowing into the workpiece. Okay, so alpha, this is positive, this is negative, this is 0. So when you use negative rate angle, more heat will flow into the what? Into the workpiece. So like what we mentioned, we wrote something about this later earlier, right? So if negative, more heat, okay, more heat going to the workpiece. Will reduce stresses acting on the tool if the material is sensitive to thermal softening. Okay, with more heat flowing into the workpiece. Okay, the possibility of generating tensile residual stresses increases. Okay, so plus and minus. Then another trend, the last trend that we're going to draw. Or I can go more. We're not really there yet. So the one more that I'm going to draw is the cutting ratio. Okay, so cutting ratio is small r. Okay, so small r is equal to small t divided by big T, where small t is the undeformed chip thickness. And small t is a constant, yeah? Constant means it's a process parameter that you define what it should be, okay? Then you have big T is the deformed chip thickness. Okay, so the deformed chip thickness is changing, and it's always a fact that small t, right, is less than big T, right? So when that's the case, R will always be less than what? R will always be less than 1. Okay. So if we were to draw a trend for this, right? So this is our cutting ratio. Okay. Alpha, 0, negative, positive. So the deformed chip thickness for negative rake will increase, right? Will be higher. The deformed chip thickness will be higher. So the trend we get is this way, right? Because if we, so this is our R trend, right? If we look at our big T trend, right? Big T, right? If I were to draw the big T trend, the big T, the deformed chip thickness trend will go like this. Okay, so this is our trend for deformed chip thickness, right? Negative rate angle will have bigger deformed chip thickness. Okay, if that's the case, I'm going to stop my lecture here. Okay, we're going to end, and today is November 26th. Okay, I will still be around if you have any question to ask me. If not, I'd like to thank you for your time, okay, and for you listening to me. Thank you.